name is Chris Harris and I'm from AlleryTutors.com, and welcome to this video on exam papers. And this exam paper we're going to look at is the OCR June 2013 Unit 4 or F324 Chemistry exam. Now the whole point of these is to go through the exam paper and write down the answers that the examiners are looking for, and along the way give you some hints and tips as to how you can improve your exam technique. And also, unlike the mark scheme, which will just tell you the answers, what I'll do is I'll actually explain why that is the answer and make links to the content as well. Learning chemistry kind of comes in two halves. One of them is the content side, so that's where you find all that in the book. And the other half of it is exam technique, and you won't find that in the book necessarily. So this video aims to go through that unique skill of exam technique and making sure that you are addressing all of the parts to enable you to successfully answer an exam paper and get you all the top marks. So it might be a good idea if you can get a hold of this paper as well. It's quite powerful if you can complete the paper yourself. And then go back to this video and then check your answers. Like I say, not only will it tell you the answers, but I will also go through and explain why it's that way as well. As you can see on the left hand side, there are a few links where you can skip to specific questions. So if you don't want to do question 1, you can skip to question 2 or 3, etc. They're all on the left hand side of the screen. So you just click on the one that you want and you should be able to skip to that question. Okay, so let's make a start. So we put these blank pages in. There we go. Right, so it says triglycerides are triesters and are found in fats and oils. It says the structure of a triglyceride found in some goat's milk is shown below. And you've got this huge molecule here. It says the triglyceride is hydrolyzed with hot aqueous sodium hydroxide. And it says give the systematic name of the alcohol that is formed from this hydrolysis. So what we need to look at is actually, you can see this section here. Now this molecule here would form your alcohol, and this one is actually called, you can see you've got 1, 2, 3, so that's going to be propane. And what we'd have is this will have a hydrogen on the end, so would this, and so would this. So it's effectively an alcohol, like the question suggests. So it's 1, 2, 3, because it's 1, 2, third carbon, and it's triol. Okay, also known as glycerol. So that's the other name for it as well. Okay, so looking at to the next part, it says draw the structures of the other organic products of this hydrolysis. So what we're going to do is we're going to look at this molecule here and come up with some of the other structures. So the first thing is we need to know is this is reacting with sodium hydroxide. So we are going to form a salt, and we know that because you can see here's one part of the molecule here. So if I just split this up. So there's one part of the molecule, there's one. And you've also got these molecules as well. So if I was to add that onto there. Now, when you hydrolyze this, you're adding water. So the water, one hydrogen would go on there, and then the OH would attach onto there to form your alcohol, which forms the glycerol. So that's why we're including this oxygen in this structure here. Because it's not water, we're using sodium hydroxide. So instead, you'd have a sodium on the end here. So I'll show you what I mean. I'll draw the structures out. So one structure would be this. There you go. So if I just pull that down, you can see it's basically this molecule here, but where we've got the O, because it's reacting with sodium hydroxide, we have an Na, so this shows a salt. You can show your charges if you want, it doesn't really matter. It just shows you that it's ironically bonded. And the other one is basically just this molecule here. So I'm just going to draw this out. except again we have an O minus and Na plus, because it's sodium hydroxide that it's reacted with, and we have CH2 for CH3. Okay, so there's your structures there. It must be a salt because we reacted with sodium hydroxide, and both of these were acids. So acid plus base will give salt plus water as well. So except in this case we're forming obviously the alcohol. So you get 3 marks for this. You get 1 for that structure, 1 for that structure, and you also get 1 mark for drawing down your salts as well. So putting your NAs in there. So you get 3 marks in total for that one. So it's not too bad. But like I say, just split up the molecule and just be logical about it. All right. Okay. So on to the final part of this question. So, suggest why people who consume a large quantity of this type of goat's milk might be more at risk of suffering from coronary heart disease. In your answer, you should use appropriate chemical terms, or technical terms, should I say, which I suppose would be chemical, and they've got to be spelled correctly as well. We'll get 2 marks for this. So, what we need to look at is perhaps some kind of, this is a type of fat. So, we're looking for something in this fat that may be linked with maybe increasing cholesterol levels in the blood, which could lead to coronary heart disease. And you can see here, if you look at this bit here, that is a trans fat. So we have a CC double bond, and we have the hydrogens that are kind of opposite the double bond like this. And this is a trans fat. And trans fats are pretty dangerous. So they increase your LDL, or low density lipoprotein, and that can increase cholesterol in the blood. So I'm just going to write that on there. So one of the fatty acids is a trans fat, full stop. And then you've got to say, because it says you've got to explain it as well, so why it might be more at risk of suffering from heart disease. Well, it says suggest why, but it's 2 marks, so we'll say what the effect is. So because we have a trans fat, this may increase the level of bad cholesterol. Okay, or you can say LDL. So anything to do with that may increase the level of LDL. Now it does say spelled correctly. Now the key term what they're looking for is cholesterol. You've got to be able to spell that correctly. It comes with the CH. If you don't spell that right, you'll actually lose that mark. So spelling is obviously important because they did state it in the question. So you get 2 marks for this. You get 1 mark for saying that one of the fatty acids is a trans fat, and then stating the effect, what effect that would have on in the blood. But there we go, 6 marks, a nice short introduction to this paper. Right, on to the next question. Okay, so this is question 2, and it says 4-aminophenol is an organic compound that can behave as an acid and a base. And you can see there's the 4-aminophenol. It says state how 4-aminophenol can behave as a base. So bases are proton acceptors, and in this case it's the nitrogen here that will be responsible for it. And on that nitrogen we have a lone pair of electrons. So we need to say here that the lone pair of electrons on nitrogen, and that accepts a proton. So that's just a straightforward definition. Okay, and then on to the next question. It says 4-aminophenol is produced by the reduction of 4-nitrophenol. Write an equation to show the production of 4-aminophenol from 4-nitrophenol. Use H to represent the reducing agent. Right, okay, so we're just going to draw our nitrophenol first. So and 2. So this is carbon 1, and that'll be 2, 3, 4. So that's 4-nitrophenol. Now what we have to do is we're going to add H. Now the H is classed as the producing agent. You've got to use that. If they've suggested that, you've got to use that. And we're forming a 4-amino phenol. So effectively, we are just getting rid of the nitro bits. So we're still keeping the phenol group, but instead up to here, amino is NH2. And right, so now what we have to do is we have to try and work out how many of these we need to turn that into that. So you can see we've got an oxygen. Now each oxygen needs 2 of these because we're forming water. We've got 2 oxygens. So we know as a final product we have to form 2 lots of water. So at least we need 2 of these for every oxygen. So we need 4 of them in total. And that will leave us with just N. But then we need 2 more hydrogens to form NH2. So in total we need 6 lots of H or reducing agents to actually make this balance. And that's really important, but that's how you'd actually work it out there. So just make sure you assign every oxygen 2 hydrogens. Okay, so that gets you 1 mark. And then on to the next bit. This is 4 marks. So these 4-nitrophenol can be produced from 4-bromophenol. So to complete the mechanism for this reaction, use NO2 plus as the electrophile and include any intermediate and the product. And it says in the mechanism for this reaction, NO2 substitutes for Br on the ring. Right, okay, so what we're going to do is we're going to start by drawing our electrophile. So our electrophile is NO2 plus, and the mechanism is going to be an electron from our benzene ring, and that goes to the NO2 plus. So it must go from the ring to there. So the electrons are going from here. It's a high density of electrons, and it goes to the NO2 plus. Okay, and we have to draw our intermediate. So effectively, this is now starting to bond with the NO2. So we're going to draw our structure. So you can see here that we've got a Br, that's still there, and we've added our NO2 on there as well. Now, because this has effectively got this carbon here in the middle, it's got 1, 2, 3, 4 bonds. It doesn't need any more electrons, so actually it pushes this delocalized structure over here, and we're left with a positive charge because the electrons from this ring have now gone in to form this bond, so there's a deficiency of electrons. Now, it's really important to make sure you draw this properly. You can see this horseshoe shape here. This end, or the end of this, does not go beyond the carbon that is adjacent to the carbon that's been bonded to. So here's the carbon that the NO2 is bonding to, and here's the adjacent carbons, and this can't be beyond that. That's really, really important. If you draw it beyond that, you lose a mark. So the electrons, obviously this is a positive charge. The bromine, it says on here that NO2 substitutes the bromine, so the bromine has to come off. So the electrons are going to come from this bond here into this positive charge in the middle there. So that's really, really important that we draw it like that. So this bromine effectively now is broken off, and the NO2 remains, and we reform our ring structure as well. So we're going to draw this, our final product. NO2, OH. And we also have our Br, but this is Br plus, because the electrons that were involved here have now gone in to form this positive, to stabilize this positive charge. So this is effectively now deficient, so we form a Br plus ion. So that's really, really important that you remember that one, because it is quite tricky actually. So, and there's your mechanism. So we've got 4 marks. So actually you get 1 mark for doing that, which is this arrow here. You get 1 mark for drawing the correct structure, and I've missed out the OH at the bottom there. So obviously I wouldn't get the mark there, but there we go. So there's your OH. And we get 1 mark for this arrow here. So that gets you 4, and then 1 mark for your final product. And so the whole lot. And you must have the BR plus as well. If you miss that out, you don't get that mark. So there's your 4 marks. Mechanisms are crucial. Arrows always show the direction of electron flow. So they must go from the area of electron density. So it must go from here to here, never the other way around, because the electrons are in that delocalized system. Okay, right. So on to the next part. Okay, so this says this is D. So it says the flow chart below shows some reactions of 4-aminophenols. So here we are here. It says identify the reagent in reaction 1. So you can see here, here's reaction 1, and we've gone from NH2 to NH3Cl, so we formed a salt. This is a base, so the only thing we would have added is an acid, and an acid with a chlorine and a hydrogen in would be HCl. So that's pretty straightforward. There you go. Okay, and then it says name the organic product of reaction 2. So it's this one here. So what we have is a phenol molecule, and we do it in alphabetical order. So we've got a bromo and an amino, which is up here. So the amino would go first because it's alphabetically it starts. So that's 1, 2, 3, 4. So that's 4 amino, and then we have on the so if this is carbon 1, 2, that's 3, 4, and 5. So we've got 3 and 5. So it's going to be 3, 5 dash, and it's going to be di bromo, and then we've got phenol. So numbers are separated with a dash between numbers and letters, and multiple numbers are with a comma. And the di tells you got 2 of them, so that's important as well. Okay, right, on to the next one. It says write the equation for reaction 2. So the equation is effectively our molecule that we had at the start. So this is your 4 amino phenol. So put NH2 on the top there. And this is going to react with, because we've added 2 bromines on there, so it's going to react with Br2. And we're going to form this product. So we've got NH2, your 2 bromines either side there, and you have your OH on the bottom. And we also form HBr as well. Now you can see that obviously we've got 2 bromines that add onto there, but there's a hydrogen that has to come off as well. So actually we need 2 lots of Br2 there, and we need a 2 there as well. And so what that means is 1 bromine from this molecule will attach itself on there, and the other bromine will then react with the hydrogen that comes off this site here, because it is a substitution reaction to form HBr. So you can see that's it all balanced there, and that would get you the mark. Okay, and then on to the next bit. It says, in the box on the flowchart, draw the structure of the organic compound formed by reaction 3. So I'm just going to pull this down here. Right, so here's our 4 amino phenol. We're adding sodium to this, and so the sodium is going to react with the OH, and you're going to form a salt. So this is going to be NH2. So remember your phenol is effectively acting as an acid. So when you react it with this metal, it will form a salt as a byproduct. So you form O minus, Na plus. There you go. And that's your formula there. So you react with the sodium and you form this salt product here. Okay, so there we go. There's another 4 marks for that question. It's quite a big question, this one. So there's 15 marks in total. 16 marks, I should say. Okay, right. On to the next part. It says E. Now it says the Sandmeyer reaction can be used to replace a diazonium group N2 plus with a halogen atom X on an atomic aromatic ring. It says the reagent used for the reaction is a copper 1 halide CuX. So you can see here, there's our diazonium group, and there's our halo aromatic compound. So it says compound C shown below can be synthesized using only 4 amino phenol and other standard laboratory reagents. The flow chart on the next page shows the synthesis. So we've got compound C there, and it says state a possible use for compound C. Now you'll see when you've got this set up here with your phenol and your azide link, we call this, or this is used as a dye. So we're going to put dyes there, or you can put something like food colouring. And that should get you the mark there. Okay. It then says, part 2, on the flowchart on the next page, we need to state the reagents and conditions used for reaction 1. suggest the structure of compound B, suggest the reagent used for reaction 2, and state the conditions used for reaction 3. And this is 5 marks in total. So let's look at our, there we go. So let's put it down there. Right, so we've got formine or phenol here, and we need reagents and conditions when it forms this. So in terms of the reactions, now obviously we are removing the hydrogens here, and we're forming our azo or azide group here. So when we do that, we have to add nitric acid, or sorry, nitrous, HNO2, rather than HNO3. So yeah, it's really important, HNO2, or you can use NaNO2 and HCl. So that can be acidified as well. So you can use either or of them. So there's either that or that. Okay, and the conditions, this has got to be at less than 10 degrees Celsius. Otherwise you get multiple substitution. And for reaction 2, so if I just bring this down here, now it's saying we're forming this and then compound B. What I'm going to do is I'm going to go to compound B first. Now to work this out, we need to look at the actual product here. Now you can see that actually we had this bit already. This bit we knew about already. So the only bit that was added on was this bit. And so that would be compound B that we bolted onto the end there. So I'm just going to draw this out just over here. Okay, so we're going to put OH there and iodine, and so that's the extra bit that was added on. Now to go from here to here, all we have to do, now it said, if I just come back to this bit, so that's why it's always useful to look back at these equations here. You can see we've got the N2 plus, and to go to the halogen, we add copper halide. So in this case, if I just come out into here, there's our N2 plus, and there's our halogen on there. So this one's going to be copper iodide, CuI, as you can see. So always useful just to go back and make sure that the answers are there. All right, and then the final step is just the conditions. So how do we get from this step here to this step here? The conditions is alkaline. So this is just the coupling reaction. So it's alkaline. Alkaline. Go. All right, so there's 5 marks available there. So we'll go through the marks. You actually just get 1 for each step, really. So we get 1 for this, 1 for this for stating the conditions, 1 for saying copper iodide, 1 for your product, and then 1 for the conditions to form the final step there. So you get 5 marks in total there. So a big question. There's 16 marks up for grabs there, but you know, not too bad. You've got to know your dyes. They're quite a common question. For your the formation of dyes using azide links. Okay, on to the next question. Okay, so this is question 3, and this is mainly concerned with polymerization and a little bit of amino acids as well. So it says many modern textiles are created using a mixture of natural and synthetic polymers. Silk is a natural fiber. It is made up of 2 main proteins, fibrin and sericin. And it says a section of fibrin strand is shown below. And you can see here, here's our strand here. It says proteins are natural condensation polymers. State what is meant by a condensation polymer. Okay, so a condensation polymer is where we have monomers. They join together. To make a polymer, and a small molecule. So that molecule could be water, it could be HCl, it could be anything that's actually been ejected from this type of reaction, but it's just a tiny little molecule. We're not talking about big chunks of molecule. Okay, so that gets you the first mark. And then on to the next part. It says a student hydrolyzed a sample of fibrin protein and she analyzed the amino acids that were formed from the hydrolysis. She found that fibrin contained the amino acid glycine, which is this one here. And it says draw the structure of the 2 other amino acids that make up the section of fibrin shown in the diagram above. So other than glycine, we need to come up with 2 other ones. So all we have to do is look at our polymer chain and try and find other ones than that. So if I start from this side, you can see that we've got an NH, a C, HCH3, COO, and then we start the NH again. So actually this structure here, so if I chop it off there, and just add the hydrogen onto the end of there and the OH onto the end of there, because obviously the water's been eliminated, so if we add them back in again, then we should get our first molecule. So we should have H2N C H CH3 C double bond O OH. So there's your first structure. So that one actually belongs up to there from that first structure there. And the other amino acid, actually if we come along, you can see we've got HNCH2 COO. So this one's actually, this next one here is this one here. And then we've got the CH3. This is the one we've already done already. And then we come to this one over here. If we keep on going, actually all the way, this one's just the same. And then this one is a little bit different. So this is a different one that we've had. So we're going to chop it off there. So there's the NH and add the hydrogen onto the end there. And then find the carbonyl group, which is there, and then we add OH on the end of there. So this is a different structure to all the rest of them. You can see it sticks out like a sore thumb, especially this group here. So we're just going to draw that structure down here. So we have hydrogen, nitrogen, hydrogen. So that's this group here. The C, hydrogen, CH2, OH, C, double bond O, OH. And so there's your final group. So this section is for that one there. You can see the structure of it. Okay, so 2 marks for this. So you get obviously 1 mark for this structure and 1 mark for that structure. So not too bad. So just look at the things. Look at your polymer chain. Make sure you add the hydrogen at the NH and the COH on the other side as well. Okay, and then on to the next part. So it says the isoelectric point of glycine is 5.8. Define the term isoelectric point and draw the structure of glycine at its isoelectric point. So basically this is the pH at which zwitterions exist. So put that down on there. Now zwitterine, zwitter means 2, or there's 2 lots or double, and ions. So it comes from the German. So it means we've got 2 ions in this molecule. And so in this case, we have a positive and we have a negative. So all we have to do is draw out glycine, but make sure they've got ions either side. So we have the structure of glycine already shown there. So we're just going to redraw that. So there's our CH in the middle there. And then we always have to have our carboxylic acid on this side. We're going to have a negative charge on there. And the proton that was here is now on here. We have a positive charge on there. So we have a zwitter ion. It's a double ion. And this would exist at the pH of 5.8, which is the isoelectric point. Okay, so you get 2 marks for this. You get 1 mark, obviously, for saying about what an isoelectric point is, and 1 mark for drawing your zwitter ion for glycine. Okay, right. On to the next part. Okay, so it says B. It says the student then hydrolyzed a section of sericin protein. She analyzed the amino acids formed using thin layer chromatography, or TLC. Name the process by which TLC separates amino acids. So the process is called adsorption with a D, because it doesn't actually absorb, it adsorbs. So make sure you use the D, absorption, which is where the chemical actually sticks to the surface, but doesn't actually get embedded within it, which would suggest absorption. Okay, and then part 2, sorry. It then says the chromatogram the student obtained and a table of RF values for amino acids are shown below. estimate the RF value for the amino acid found at X, and hence identify the amino acid found at X. So what we have to do is measure the distance from the baseline to X, and then divide that by the distance from the baseline to the solvent front, and that should tell us the RF value. So we get our ruler, and we're just going to measure that. Now they do say estimate because it depends on if you're measuring from the bottom or the top of the dots. It doesn't really matter. I'm going to say that's 2.5. So I'm going to put 2.5, which is on there, and then we're going to measure the distance from the top there. So again, I'm going to say that's about 4.5. So I'm going to divide that by 4.5. Now, if we got a calculator, 2.5 divided by 4.5 gets us 0.56 if we had to round that up. There you go. So, and this, if you look in our table of data, 0.56 sits close to this one, methionine. So we're just going to put the amino acids. Okay, and actually, if you look at the mark scheme, they will accept any number between 0.53 and 0.62. So if you've got a number that falls between that, then you should still get the mark as well. But there's 2 marks up for grabs there. So you obviously get 1 for your calculation and then 1 for identifying the amino acid. So it's not bad, really. You know, they've given you the data of RF values. You've just got to remember how to work out the RF value. Okay, and then on to the next one. So this is part C. It says Kyana is a synthetic polymer that can be spun into a soft silky fabric. The monomers used to make Kyana are shown below, and you can see we've got 2 molecules there. And then it asks, draw a repeat unit of the polymer formed from these 2 monomers. So we've just got to draw the 2 together, combine them, and emit the water that's being kicked off from them. So I'm just going to push that up so we can get some space. So all we're going to do is we're going to actually chop off the water here. We're going to chop off the OH there, and we're going to take one of these hydrogens away and join the NH with this group here. And again, we're going to chop off one of the hydrogens there on this side because we're obviously going to form polymer. So where we've chopped them bits off, we have to draw it with a dotted line to show it. So I'm going to draw a dotted line there and draw a line going down, double bond oxygen, that's this bit here, CH2 6, and then we're going to draw the line going up and then down, double bond oxygen. The OH is gone completely because that's reacted with the hydrogen from here. So we have a nitrogen there with a hydrogen still attached, and we draw this structure here. And then on this side, we have NH still, and then the dotted line, which will make sure it goes across. Okay, so we've got 2 marks here available. All we've done is I've just emitted the water from either side. So you actually get 1 mark for drawing this bit here. Now this is your, there you go. This is your NH double bond. Oh, so this is your amide link, and that gets you 1 mark for showing an amide link. And you get 1 mark for the general structure as well, for structuring it properly. So that's where you get your 2 marks from. All right. Okay. So on to the next bit. Okay. So we've got question D, or part D. It says polymer D has been developed by the textile industry. The repeat unit of polymer D is shown below. And here it is here. It says polymer D is a condensation polymer. Draw the structure of each of the monomers that make up polymer D. All right, so again, we just have to show the monomers that make it up. So we're going to add the hydrogens to it. Now you can see here, we're looking for these links here because this is where it would have joined on. So I'm going to break it there. Now this would have been perhaps an alcohol. It does say it's a condensation polymer. We have an ester link here. So we have to have an alcohol and a carboxylic acid. So this would have been a diol. So you would have hydrogen there and a hydrogen there as well. So I'm just going to draw this out. There's our oxygen. Okay, so there's that molecule. And then this one would have been a dicarboxylic acid by the looks of it. So we're going to add the OH on the bottom there. Double bond oxygen, which goes there. There's a double bond there. And you have a double bond there. And then you have an OH on the end like that. So that's what it should look like, and you can see the OH would have gone onto there, and then the OH would have been on there. So I've literally just added our OH groups on there, and that gets you 2 marks. So you see, polymers are not too bad. You've just got to make sure you know where to break the molecule. You've got to identify that as well, so that's pretty crucial. All right, okay, and then on to the last part of this question. So it says polymer D reacts with a third monomer to form an addition polymer. The repeat unit of this polymer is shown below. So you can see here's our, if I just bring it down to spot the difference. So you can see here's our original polymer and here's our new one. So what we've done is effectively added it here. This double bond has opened up to form a bond here and then a hydrogen there. You can see there's the hydrogen. And then this molecule has obviously had to have a double bond as well because the double bond is actually opened up to form a link there as well. So what we need to do is we need to draw in our molecule, but the double bond on this molecule must be here because it's opened up to form a bond here. So we're just going to draw out basically the same molecule, which is this bit here, this bit, but it must have a double bond. It must have had a double bond here because you can see that's extending outwards. So we're going to draw a structure. Okay, and then this goes down there, and we've got a double bond. We must have that double bond there. And so there is your addition monomer, your third monomer that's actually added onto that molecule. And that just gets you obviously the 1 mark there. Okay, so this whole question was out of 13. A lot of polymer stuff on there. Polymers aren't that bad, but you do need to make sure you know where to break them and what you're drawing as well to make sure it makes sense. But on to the next question. Okay, so this is question 4, and it starts by saying compound E, shown below, is an alcohol that is found in oak wood. It is formed by the breakdown of cellulose. So you can see here's compound E here. It says compound E can be converted into compound G as shown in the flow chart below. So you can see here there's compound E and there's our reaction 1. And if we move on down onto the actual question, it says complete the flowchart to show the structure of the organic compound F and the reagent needed for reaction 2. So just put that down there. Okay, so it says complete the flowchart to show the structure of the organic compound F, which goes in here, and the reagent for the next step for reaction 2, which goes in there. Right. So what we're going to do, I'm just going to push that up. So there's our compound E. We're adding excess dichromate and sulfuric acid, and the excess tells us that, and it's all in reflux as well. So it tells us that this primary alcohol here is going to convert into a carboxylic acid because it's going to go all the way, and this secondary alcohol here is going to convert into a ketone. So because we've got enough dichromate for it to do that. So we're just going to draw out this molecule here. So it's going to be 1, 2, 3, 4. And then at this point here, this obviously goes up. So at this point, this OH turns into a ketone, as you can see there. And this will bend round. We have our methyl group there. This is our wedge. And you've got to draw it as the wedge as well. So that can't change. And once we've done that, then we just need to add our carboxylic acid on there. There you go. And so there's your final product. And that's F. Okay, and then it says we need a reagent for this as well. If I just nudge that up so we can see them, you can see if we look at the difference here, the only thing that's actually changed is this. So this group here has actually been, well, it's effectively been reduced. It's gone from a ketone to an OH. So, but it's just it hasn't actually affected this. So the reagent we'd use is a reducing agent, something like sodium borohydride, NaBH4. Okay, and so that's your reagent that you would use there because it shows a reduction process. Okay, right, on to the next part of this question. Right, so it says, what would you observe during reaction 1? So reaction 1, remember, if we just come back to it, is this one here. And you can see dichromate is actually a coloured compound. Dichromate is orange. And when the dichromate is reduced, which it is in this case, because we're oxidizing our alcohol to a carboxylic acid and our secondary alcohol to a ketone, this itself is reduced. And so this is reduced to chromium 3 plus, which is green. So we actually get a colour change. So that's a classic sign that the reaction has happened because the actual oxidizing agent actually changes colour. So we get a colour change. So colour change, and that goes from orange to green. You must be specific. You've got to say what it goes from, what it goes to. Okay, part 3 says in reaction 1, compound E was heated under reflux with excess dichromate and sulfuric acid. Suggest why these conditions were used rather than the reaction mixture being distilled during this process. And what we need when we reflux, we actually allow the dichromates to oxidize any alcohol fully all the way to a carboxylic acid. If we distill it, we'd actually get an aldehyde formed instead. But we wanted the carboxylic acid, so we just put it in the reflux and get it heated up. So, so the answer would be to make sure carboxylic acid was formed. We don't want any aldehyde formed, so there you go. Right, okay, on to the next one. It says, name the type of reaction taking place in reaction 2. So if we bring it back again, there's two possible answers really for this one. You can see here that we've gone from from this molecule here, we've used sodium borohydride to form this. This is a sign, you can see there's our ketone there, and there's our alcohol there. And so this is a sign of reduction. Or you could say nucleophilic addition as well. Whatever you fancy, really. All right, okay. So next one, which is B, and it says describe a chemical test that you could use to detect the presence of a carbonyl group in an organic compound. So we are needing our reagent. So we're testing a carbonyl group, and a classic reagent which would do that is 2,4-DNPH of dinitrophenylhydrazine. Or you could also call that as Brady's reagent. Okay, right. And what would you see? You'd see an orange precipitate formed. Now, it's very important that you obviously give the colour change and that you state that it's a precipitate that's formed. It's no good just saying it goes orange. You've got to be really specific because it does ask about an observation. Okay, so you get 2 marks for this. You get 1 for suggesting the reagent and then 1 for stating your observation, which is the precipitate that's formed. Okay, and then on to the next part, which is C. Says compound E is a single stereoisomer. Draw the skeletal formula of one other stereoisomer of compound E and state the type of stereoisomerism. Right, so I'm just going to bring that in here. So you can see there's E there, and there's no double bonds, so we don't get any geometric isomerism where we have any EZ. So the only other type of isomerism we can have is optical isomerism. So, and the reason why we can have that is because we have a carbon with 4 other groups attached to it. So, for example, this carbon here would be chiral. So you've got this group down here, you've got this group along here, you've got the methyl group, and then you've got a hydrogen. So because we've got a chiral center, then we can have optical isomerism. So all we have to do is just draw a mirror image of this molecule here. So I'm just going to fold that back. I'm just going to show you how easy this is. So there's our molecule there, and we're literally just going to draw a mirror image of that. So we're just going to start with, no, it's a bit weird because you're going to have to do this kind of back to front. So we're going to do down, which is down to there, and then up, and then down, and then we have our wedge here, but we're going to draw this going down there first. So there's our wedge, which is going down there, and then we have our molecule. Now this one is effectively starting to kind of move away, so we're going to draw this side. So we're going to draw a line going down, which is there, and then up, and then down, and then up again, which is there. And then coming off this one here, we have our OH. There you go. And you can see that's not bad. That's pretty much a mirror image of that. And so if we had to put a mirror line down there, and if I had to put a mirror, it is pretty much like a reflection. And that's all you have to do. There's nothing kind of special about it. And the type of stereoisomerism is optical. There you go. And so that kind of shows you how to draw it as like a mirror image. There's my art skills coming through. Not. Okay, so this is an optical isomer. And this is going to be 2 marks. So we're going to have 1 mark there and 1 mark there. And there we go. There's your 2 marks. Okay. And on to the next bit. Okay. So this is part 2. And we've got a little bit of maths here. So it says a 4.56 gram of compound E was converted into compound G using the method shown in flowchart on page 12. It says 3.15 grams of compound G was formed. Calculate the percentage yield of compound G and give your answer to 3 significant figures. And the MR of compound E is 160. Right, so when we're working out a yield, we have to work out the number of moles of our product at the start and the number of moles at the end, and we divide them, times it by 100 to get a yield. So we're going to start with working out the moles of E that were used. So we said that we had 4.56 grams. So it's going to be mass over MR. And we've been given the MR actually of this, which is pretty useful. So that's just 160.0. And if we put that into our calculator, okay, so that's going to be 4.56 divided by 160.0, 0.0285. Okay, let's put mole in the end. Right, and then we need to write down the moles of G. This is formed. Okay, and so the mass it says here was 3.15. Okay, and that's in grams. And you divide that by the MR. Now you have to work that out for G. So if I bring this back in, there was G there, which was on the bottom. So now for quickness, I've just worked it out already, and it's 174. But you can obviously use the periodic table to work that one out. I'm sure you'd be able to do that. And then if we put in 3.15, we divide that by 174. We should get 0.0181. And that's in moles. All right. And then the yield is basically the number of moles of your product divided by the number of moles that you had of your reactant. So that's going to be 0.0181 divided by 0.0285 times that by 100. And we should get our final answer. Move that to one side so you can see it. So it's 0.0181 divided by 0.0285 equals, times that by 100. There you go. and that should give us 63.5%. And it must be to three significant figures, so we don't want to give any more than that, otherwise we'll lose our mark. So that's 63.5%. Oh, you don't have to put the percent sign in because it's already there. Okay, so marks, 3 marks for that, which is not too bad really. It seems as though it's just a bog standard mole calculation. But moles of E is you get 1 mark for there, 1 mark for moles of G, and 1 mark for your working out your percentage. So you get 3 there in total. Okay, right, and now to the last bit of this question. So this is part 3. Compound G is heated for several hours under reflux in the presence of a concentrated sulfuric acid catalyst. So we've got a reflux here, and we've got concentrated sulfuric acid catalyst. An ester and a small inorganic molecule are formed. Complete the reaction to show the 2 products formed by this reaction. So this is effectively your acid catalyst. Now, normally to form an ester, you do carboxylic acid plus alcohol will give ester plus water. So our molecule that we're actually forming has got to be water, because all esterification reactions produce water. So there's our little inorganic molecule, should I say. And now this is a bit weird because actually we've got 1 molecule, but there's our alcohol and there's our carboxylic acid. It's all attached to the same molecule. So what we have to do is do a reaction where we eliminate the water from here. So the H there and the OH there. This will then go off to form your water molecule, and all the rest will just join round to form your ester. So let's draw the molecule. So it's 1, 2, 3, 4, 5, 6. Draw your wedge. So we're up here now, and then down, and then down, and then these 2 here, you'd have your oxygen, which is there, and at this point here, you would have your double bond O. So there is your ester, which is on that bit there. So yes, make sure that's drawn correctly, and make sure you have your wedge in there as well. That's very, very important. So yes, that's what you would form. The acid catalyst is classic. Sulfuric acid is a classic catalyst that you'd use to form esters. Okay, so you get 2 marks for that. It's a bit weird because you've got this kind of funny cyclic business going on here. But you are still forming an ester. They're just doing it a bit differently. That's all. I would imagine a lot of people might have missed that, or they might think, "What on earth's going on here?" But it's not too bad. You get 2 marks there, so 13 marks in total. So unlucky for some, but I hope it was lucky for you. So on to the next question. Okay, so this is the last question, and this is question 5. And it starts by saying a chemist isolated compound L from the leaves of a common garden herb, and he analyzed the compound using a number of techniques. So compound L contains CH and O only. Elemental analysis shows that L has the percentage composition by mass of carbon, which is 73.15%, and hydrogen, which is 7.37%. The mass spectrum of L has a molecular ion peak at MZ164. So show the molecular formula of L is C10H12O2. Right, so the first thing we need to do is we need to work out our empirical formula. They've given us the percentage composition of this element, so that's what we're going to do first. So now one way, which I think is probably the easiest way to work out empirical formula, is by writing the elements as a heading at the top like that, and then we're going to take the masses of each of these. So this time they're given us percentages, so that's 73.15. Hydrogen was 7.37, and then oxygen, they haven't told us what that is. That's not a problem. All we do is we add 73.15, and we add that to 7.37. We get that, and if we subtract that away from 100, we get 19.48% for oxygen. Now, we'll divide each of these by their MR, or the AR, should I say. The AR for carbon is 12, and hydrogen is 1, and oxygen is 16. So if you're not sure, you can obviously look at the periodic table for that. And then what we're actually doing there is effectively working out the number of moles. So we'll work out them now. So that's 73.15 divided by 12, That's going to give us 6.09, or just put 6.10. So that's what it rounds up to. Obviously, this is going to be 7.37 because that's just divided by 1. And then oxygen is going to be 19.48 divided by 16. And that's going to give us 1.22. We'll just round that up, like I say. Okay, and then what we do is we find the smallest number of moles and divide them by the smallest number. This is the smallest number, so we're going to divide all of them by 1.22. Obviously, that's going to give us 1 for the oxygen. And then this one, I'll just pull that up on there. So this one's going to be 7.37 divided by 1.22. And that's going to give us 6.04, so that's just going to round up to 6. And then if we go on to the other side, 6.10 divided by 1.22, 5. So that's a straight up 5. That's going to make it pretty easy. So the empirical formula is C5H6O. Now they've said that the molecular mass of this compound is 164. Now if we take the mass of this, so if we do 12 times by 5 for the 12 carbons, plus 6 for the hydrogens, and we're going to add that to 16 for our oxygen, then we should get 82. Now, you can see 82 is just half of 164. So what we need to say is, so if I just move that up, MR is 164. So molecular formula, and this would be effectively just double, because that would be C10H12O2. So if we double each one of these, then we'll get our formula there. So we get 2 marks there. You actually get 1 mark for working out your empirical formula, and 1 mark for saying that the molecular formula and trying to link it together. So you get 2 marks there in total. Okay, right, on to the next bit. Right, now this is NMR, which can be a real pain sometimes. I know some people absolutely hate it. So it says the carbon-13 NMR spectrum of compound L is shown below, and you can see here there's our carbon-13 spectrum. How many different carbon environments or types of carbon are present in a molecule of compound L? So this is dead easy. All we have to do is just count the number of peaks, because that tells us the number of environments that we have. So we have 1, 2, 3, 4, 5, 6, 7. 7. There's your answer. Okay, and then your proton NMR, which is the next bit, says the proton NMR spectrum of compound L, C10H12O2, is shown below. One of these signals has been enlarged to help its analysis. So you can see here that we've got 3 different environments here, and we've got this splitting pattern as well. So this is your multiplet, and then we've got a double peak here, and we've got one here as well, but we can't really read that. And there's our integration traces that show that. All right, okay, so if I'll just put that to one side because we'll probably need that later on. Okay, so it says, a signal at sigma 0 ppm results from tetramethylsilane, or TMS. TMS had been added to the sample of compound L before the NMR spectrum was run. State why TMS was added. So TMS, as tetramethylsilane, is the reference. So we measure everything relative to that. So reference. Okay, right, and then on to part 2. It then says the proton NMR spectrum includes an integration trace. What information can be deduced about compound L from the integration trace? So if I just bring it back again, so there's our integration trace there. Now you can see that we have basically 3 hydrogen environments, and the ratio of these hydrogens is 5:1:6, and that's basically what it's telling us. So just going to put that on there. So we've got 3 hydrogen environments in a 5:1:6 ratio. All right, okay, and then on to the last part of this question. This is a big question. This one's worth 7 marks. It says using the information given in parts A, B, and C of this question, determine the structure of compound L. Show all your reasoning, and in your answer, you should use appropriate technical terms spelled correctly. Okay, so what we're going to need for this is we're going to need our data sheets, and we're going to need our proton data sheet. So if you have your data sheets, which might look something a little bit like that, and you'll need to turn to your NMR pages. So you can see here. So it should look something like that with your different NMR parts. So what we're going to do is we're going to try and identify what's in here. So we were given a carbon-13 spectrum first, so that's what we're going to use. You can see here, here's our carbon-13 one at the bottom. So let's have a look at our spectrum. Let's bring it back. Right, now we've got a few significant things here. We're going to start with maybe looking at this peak here. Now this one is roughly at about somewhere about 185. So this one's furthest to the left. So if we have a look on our data sheet, it's telling us that something at 185 is going to suggest either this group or this group, which is an amide, or some kind of carboxylic acid group or an ester. So it's telling us that we can't have this because our molecule suggested we don't have an N in there. So actually, we must have this group set up here, a carbon with a double bond oxygen and then an O here. And it's telling us there's something here and something here. So let's draw that out. Let's write that down first. Okay, so carbon-13 NMR. So the first thing we have is we have a peak at 185 ppm, and that would suggest an ester group. And this is obviously what we had. With this carbon obviously being what the NMR machine is picking up. And then we've got if we come back to this, you can see we've actually got a bunch of ones around this region as well. So if we bring back our data sheet, somewhere between like the 120 and kind of like 160 mark, like around here, we've got a lot of peaks around here. So if we bring back our carbon-13 and see what we've got here, so you see here between the 120 and 160, we've got this, which is a benzene ring. So that's a massive giveaway that we've actually got this here. So we're just going to write that one down as well, because that's obviously really important. That gives a lot away, tells us a lot about structure, and it uses a lot of the carbons up as well. So I'm just going to write that down here. So we say the peaks between 120 ppm and 160 ppm indicate benzene ring. All right, okay, so I think we've probably got enough from the carbon-13 to give us an idea of what we've got. So we know we've got a benzene ring in there, and we know we have to have an ester. So they're the two key bits there. So we've actually found out quite a bit just from the proton NMR. We don't know a lot about the structure though, how it's been arranged. So that's what we're going to need proton NMR to do. So we'll just get a bit more space. Okay, so let's, you see they've given us a big load of lined paper here, so there's plenty of space. So we're going to look at proton NMR next and see what that can tell us. Right, so let's bring this back in. So there's our spectrum. Now what we have, you can see, we'll start on this side on the right. We have a doublet, and this is at about 1.2. And so we're going to try and find out what this is. Now you can see the integration here is quite high. So this suggests that we've got 6 protons in this environment. Now to have that many protons, would normally suggest we have two CH3 groups, because you can't physically have 6 protons around 1 carbon. So we have two CH3 groups bonded to a carbon, but they're bonded to the same carbon. So that's a big giveaway there. But we'll see what that is first, that 1.2. So if we bring in our data sheet, so you can see here our 1.2 would suggest this group here, which is a CH. So we've got a CH, and this proton is next door to well, there is one, these protons, this kind of doublet has 6 protons, but it's next door to a 1 proton. That's why it's a doublet. So we're going to write that down on there. So remember, the splitting pattern tells us what's adjacent to these 6 protons. So the doublet tells us that it's next door to 1 proton according to the n+1 rule. So what we're going to put in here is we're going to say we have a doublet at 1.2, and that shows our RCH, and the H, this is what the NMR machine is picking up, is the hydrogen. And it also shows us that we have 6 hydrogens, or we can say 2 lots of CH3. So we can say that these 2 lots of CH3 are next door to a carbon with a single hydrogen on it, and so that's what we're suggesting here. Okay, and if we look at the next peak, right, we have this multiplet or heptet, which is here. Now, this indicates, this is going to tell us that actually this one hydrogen, only has 1 hydrogen on it, is next door to 6 other protons. Now, this could be actually these protons here, because it seems to match. So we're just going to write that down, what we've observed first, or what the spectrum is telling us, and then we'll start and piece it together later on. So we have a multiplet, or you could say a heptet, multiplet at, I think that was 2.7, yeah, 2.7 ppm, and that indicates, so let's have a look. Okay, so you can see here we're looking for one at 2.7. So we can see that we have this group here. This would be 2.7, so it's quite high up. So it indicates this type of group, and that would fit in because we've got 1 proton there, and that's next door to a carbonyl group. So we're just going to put that in there. Okay, H, C, C, double bond, O, with our group there. So that's what the multiplet suggests. Now it suggests that this is 1 hydrogen, which is right, but next to it we probably will have 2 CH3 groups, because this is next towards 6 hydrogens in total. So that's probably the likely structure there, but we'll come back to that and see if that's correct later on. And then the next peak, which we'll come on to in a minute. I'll tell you what we'll do is we'll write down this doublet first. Just going back to this one, because it seems to flow a little bit better. So the doublet suggests 2 CH3 groups. Attached to a CH, which is this one here. So there's the 2 CH3 groups attached to the CH, which is the multiplet. So basically what we've said is we're just telling the examiner that we think we've got, which is this proton here, and we have 2 CH3 groups either side here, because this has been split into 7, which suggests it's next door to 6 protons. So that's what we're trying to say there. We've got 2 CH3 groups. So what we're trying to do is try to form the structure of this thing. Okay, and then if we bring back our spectrum, and we'll have a look at this peak here. So we've got one at 7.3. So and this has got 5 hydrogens. Now, we found out from carbon-13 that we had a benzene ring. So we just bring in back to this, and we'll just see what the 7.3 might tell us. And yes, certainly does. There you go. There's your benzene ring with your proton. We know it has this, and it says that we've got 5 of them as well. So that suggests that we have a group. One of the protons has now got a group coming from it. So I'll just write that down. Okay, so we have, let's put that there. So we have a peak at 7.3 ppm, indicates a benzene ring. And it also tells us that we have 5 hydrogens as well. So all we've done is you just stated what it stands for and how many hydrogens it's got. And so what we can start and do now is we can start and form our structure together. So we know we've got a benzene ring, so we're just going to draw that there. And we know that this benzene ring has 5 hydrogens. So that means one of them is being taken up by our single bond there. And then we also know that we have an ester, but we know that actually this H here is bonded to 2 CH3 groups, which is next door to the C double bond O. So this bond here must be an oxygen because it's going to be an ester. So when we draw this, I'm just going to flip this over. We're going to put the oxygen there, and we're going to have our carbon there with the double bond. And then, because we found out from the structure that we had a carbon there with a hydrogen that was attached to it, and then attached to that was 2 CH3 groups bonding off it. So this is actually the structure of our molecule. You can see we've kind of pieced it together over time, and you can check that to make sure that matches as well. So we've got C10H12, so we've got 6 carbons there, 7, 8, 9, 10, H12, 3, 6, 7, 8, 9, 10, 11, 12 hydrogens, and then we have 2 oxygens which are there. So that fits the molecular form in it as well. So all we have to do now is just write in our answer into this box here, and this is going to be something like this. There you go, and that's your molecule there. So in terms of marks, you actually get 2 marks for the structure. Again, just make sure you're kind of doing these correctly. So there's your 2 marks there. You also get 1 mark for talking about the peaks in the carbon-13 NMR. So there's 3. And then if we come into this one, your proton NMR, you actually get 1 for stating about the doublets, 1 for the multiplets, and then 1 for trying to hint at the what these two kind of mean. So the doublet suggests 2 CH3 groups attached to a CH, which is the multiplet. So we're trying to form structure here, and then you get your final mark for actually talking about what the last peak is at 7.3. But NMR is pretty tricky. Make sure you know how to do it. Now, like I say, I've got a YouTube channel that looks into NMR, and it tells you how to work it out. So if you're not sure, you can have a look at the NMR videos that I've done, and it has a bit more of an explanation. But there we go. There's 12 marks in total for that last question. So that's the end of the paper. Bye bye.